Hello everyone, welcome back to our channel. Today we're going to explore a fascinating and critical aspect of cancer research, viewing cancer as a metabolic disease. This perspective not only deepens our understanding of cancer, but also opens up innovative avenues for treatment. We'll discuss how cancer cells rewire their energy production and look at potential therapies that target these metabolic differences. Understanding cancer as a metabolic disease. Let's start with the basics. Traditionally, cancer has been considered primarily as a genetic disease characterized by mutations that lead to uncontrolled cell growth. However, recent research has highlighted that metabolic dysfunction also plays a crucial role in cancer development and progression. This approach examines how cancer cells generate and utilize energy differently from normal cells. Mitochondria and energy production. Mitochondria, often called the cell's powerhouses, are essential for energy production. In healthy cells, mitochondria generate energy through oxidative phosphorylation, which uses oxygen to convert nutrients into ATP, the cell's energy currency. This highly efficient process supports the cell's energy needs for various functions, including growth and repair. The Warburg effect. However, cancer cells exhibit a notable shift in energy production. They often switch from oxidative phosphorylation to a less efficient process known as glycolysis, even when oxygen is available. Otto Warburg first described this phenomenon in the 1920s. But why do cancer cells prefer glycolysis? Glycolysis allows cancer cells to produce energy quickly, even though it's less efficient. This rapid energy production supports cancer cells' fast growth and division. Moreover, the byproducts of glycolysis can synthesize the building blocks needed for new cells, such as nucleotides and amino acids, which are essential for cell proliferation. Metabolic flexibility of cancer cells. One reason cancer cells can thrive is their metabolic flexibility. They can switch between different metabolic pathways to adapt to varying environmental conditions. For example, cancer cells can increase glycolysis in low oxygen environments to maintain their growth. This adaptability makes cancer cells resilient and challenging to target, with treatments focusing solely on one metabolic pathway. Therapeutic strategies. Targeting metabolic differences. Understanding these metabolic shifts provides a unique opportunity to develop targeted therapies. Here are several strategies being explored. 1. Inhibiting glycolysis. Since cancer cells heavily rely on glycolysis, inhibiting this pathway can effectively starve them of energy. Glycolytic inhibitors like 2-deoxy-D-glucose, 2-DG, and dichloroacetate, DCA, are being studied for their potential to disrupt cancer cell metabolism. These drugs inhibit vital enzymes in the glycolytic pathway, reducing the energy supply to cancer cells and slowing their growth. 2. Targeting mitochondrial function. Some therapies aim to restore normal mitochondrial function in cancer cells, forcing them to switch back to oxidative phosphorylation. This can increase their susceptibility to stress and trigger apoptosis, the process of programmed cell death. Agents like metformin, commonly used to treat diabetes, have shown promise in targeting mitochondrial pathways and reducing cancer cell viability. 3. Exploiting reactive oxygen species, ROS. Cancer cells often produce high levels of reactive oxygen species, ROS, due to their dysfunctional mitochondria. While low levels of ROS can promote cancer cell survival and proliferation, excessively high levels can be lethal. Therapies that further increase ROS levels in cancer cells, such as pro-oxidant drugs, can push these cells beyond their oxidative stress threshold, leading to cell death. 4. Nutritional interventions. Dietary strategies such as ketogenic diets are being explored as potential adjuvant therapies for cancer. These diets drastically reduce carbohydrate intake, limiting glucose availability and forcing the body to rely on ketones for energy. Since cancer cells struggle to utilize ketones efficiently, this metabolic shift can help starve cancer cells while providing energy to healthy cells. Challenges and future directions. While targeting cancer metabolism holds great promise, there are significant challenges. Cancer cells are highly adaptable and can develop resistance to metabolic therapies. Therefore, combination therapies that target multiple metabolic pathways simultaneously are being investigated to overcome this resistance. Moreover, cancer cells' metabolic requirements can vary widely depending on the type of cancer and its stage of progression. Personalized approaches that tailor metabolic therapies to a patient's specific metabolic profile are crucial for effective treatment. In conclusion, viewing cancer as a metabolic disease provides valuable insights into its development and progression. By targeting the unique metabolic needs of cancer cells, we can develop innovative therapies that are both effective and selective, sparing healthy cells in the process. This approach enhances our understanding of cancer and offers new hope for better management and potential prevention of this complex disease. Thank you for watching. If you found this information helpful, please like this video, share it with others, and subscribe to our channel to stay updated with more educational content on managing cancer and improving overall health. Don't forget to hit the notification bell so you never miss an update.